Okay, hello everyone. It's our great pleasure to welcome Thomas Dreyfus, who will give a talk this afternoon, or this morning, I should say, on differential transcendence and shift equations.
Yeah, so thank you very much for the kind invitation. So for me, it will be the afternoon, almost the weekend. So as I say, I'm not able to see the chat. So if you have a question, please interrupt me. I will be very happy to try to answer, at least try to answer. So today I will speak about the continuation of a previous work that I had with Boris Adamczewski and Charlotte Ardouin. I think I've given a talk here in Colchin online. The first 15 minutes of the talk approximately will be devoted to a reminder of what we made with Boris Adamczewski and Charlotte Ardouin, and then I will explain what is new and what I did. So in the number theory, so the most common field you can imagine is the field of rational number, and you have a notion of algebraic number. And if you want to make the counterpart of this in the background of a function, Q, the most natural field of function is the rational function. So I take rational function over C for reasons that will appear. And you have a notion of algebraic closure of C of Z, which are the field of algebraic function. But in the situation of the function field, you have another notion. You have the notion of derivation. So you can make classification a little more precise, and it's bring you to new class of functions, so the holonomic one and the differential algebraic one. I will give the definition of everything in 2 minutes. And so today, by a function, I mean very vaguely Pizzo series somewhere. So let me give more precise definition. So I say that f is algebraic if and only if it vanished non-zero polynomial. So it's a very classical notion. Normally, everyone should be very used to it. So for instance, square root of z is an algebraic function. And we say that f is holonomic if it's solution of linear differential equation. So some people used to say definite. I will say holonomic in this talk. So you know a lot of examples of functions that are holonomic. So for instance, the logarithm, the exponential, every algebraic function are holonomic. So you have a very large class of functions that are holonomic. So holonomic functions form a rings, and unfortunately, it does not form a ring. So the most common example you have in mind is tangent. So it satisfies an algebraic differential equation. So if you want to have a field, you have to consider algebraic differential equation, and so it's bringing you to the new notion. So I say that f is differential algebraic if there is a non-trivial algebraic relation between f and its derivative. So the most common example of differential algebraic function is p various function. But for instance, you have generating series of works in the quarter planes that are differential algebraic. So you have a very nice paper of Bernardi, Busquet-Melou, and Rachel about it. And I will say that f is differentiate transcendental otherwise. So like in the number theory case, if you consider a complex number, normally it will be transcendental. And if you consider a pure series, normally it will be transcendental. So the world of differential algebraic function is quite small. And the goal is to prove that it's very, very small. So you have algorithm to test if a function is holonomic or not, but you have no effective algorithm to test if a function is differential algebraic or not. A reason of that is there are too many unknowns, so it's too complicated to deal with the bounds. So let me focus on some smaller background, so the background on difference equation. So you have a proof of differential transcendence some function. So the older one is due par order for the gamma function. So the gamma function is differential transcendental. And so I've given two other examples, f1 and f2. So f1 is a Q-apart geometric function, and Ardoin and Singer prove that it's differential transcendental. And f2 is solution of a Malor equation. So both functions I've given here are solution of a functional equation. So the first one, so z maps to z plus 1. The second one is z maps to q of z. And the third one is z maps to z squared. So we might wonder if a solution of a difference equation is necessarily differential transcendental. And if we think to this few minutes, we arrive at the conclusion that it cannot be true. So you have very easy counter example. So for instance, exponential is solution of a shift equation. Logarithm is a solution of a Malor equation. And the q theta function is solution of a q difference equation. And both functions are differential algebraic. So to be more precise, we will have to be a little more careful. So the general idea of the theorem is that if you consider a function solution of a linear functional equation and that belongs to a certain field, then it's differential transcendental. And so the main point is to choose very carefully the field. So for instance, if you consider a shift equation, you have to eliminate the exponential. If you consider a Malor case, you have to eliminate the logarithm, and so on and so on. So let me give the difference framework that I will consider in this talk. So Y will be a function, so a series belongs to a field F, and that will be solution of linear functional equation. And let me consider four cases. So the first one is a more natural one. So Rho is a map that sends y of z to y of z plus h, where h is a non-zero complex number. So such kind of equation are called difference equation or finite difference equation. The second one is that I will call case S prime, is when you take formal series at infinity, so still the same row. And the third case, when you consider formal Piso series, and then the map that sends y of z to y of qz. And here you need that q is not a root of unity, because I want to avoid the situation where rho is cyclic. And the last case, which calls the Malorian case, is when rho is sort like a Frobenius automorphism. So this last case is particularly interesting because it has been proved that if you consider a solution of a Malor equation, and most of its transcendental values are transcendental. I mean, the function applied to a transcendental number is transcendental. So it's like Lindenmahl theorem for exponential that says that the exponential of 1 or 2 are transcendental number. And this kind of theorem is very powerful because it used to be very complicated to prove that a number is transcendental. So the Malloy situation gives you a very large class of examples. So in the work with Boris Adamczewski and Charles Tadouin, we deal with the case S prime, Q, and M. And today I will deal with the case S, and I will show you that there are some subtleties that make it a little more complicated. So let me give some reminders of already known results. So the first natural question is to deal with the dichotomy between being holonomic and being not holonomic. So let Y be a solution of a linear whole equation. And the theorem says that if either f is rational or as is y is non-holonomic. So the original proof in the case Q was made by Ramis and in the case M by Bézivin. So they prove this theorem totally independently. And in a more recent paper, Shafku and Singer give a very unified way to see this theorem. And they prove the theorem for the case Q, M, and S. So we have the first dichotomy. So if Y is a solution of a linear differential equation, a linear functional equation, then it's very simple. It cannot satisfy linear differential equation, otherwise it's trivial. Okay, so now let's move on to the differential algebraic case and affine order 1 equation. So still consider Y, that is solution of rho y equals AY plus B. And then either Y belongs to the ground field or Y is differential transcendental. So this kind of result go in the same way, meaning that if you are differential algebraic, then you are extremely simple. So again, the case Q and M were treated separately and independently. And this time with Adamczewski and Hardware, we give a unified proof to consider the case S prime with Galois theorem. So originally the proof was made just by. Are you able to hear me? It's okay? Hello?
Yes.
Okay,
Yes.
great.
Yes.
Just wanted to check that everything worked. So originally the proof was made by just considering the functional equation. You assume that Y is solution of a differential algebraic equation, and then you play with the two equations, and you prove that Y must be too simple. Okay, so if we want to move from order 1 to order n case, this kind of reasoning could not be treated because already for the order 1 situation, it's extremely technical. So if you jump to the arbitrary order, it will be impossible to handle. And then Ardoin and Singer develop a Galois theory that aims at understood what are the algebraic differential relation satisfied by functional equation, by solution of functional equation of this kind. So roughly speaking, this group, their group attach to the equation a differential group. Bigger it is, and less algebraic and differential relation you have among the solution, and the goal is to prove that this group is sufficiently big. And with this strategy, with Charles Tardouin and Julien Roch, we prove the following theorem in the case M and Q, and then Arashi and Singer deal with the case S. Under the assumption that the equation has a difference Galois group that contains SLN, so the classical difference Galois group, either Y is 0, either is differential transcendental. So this result is quite surprising because you have an assumption of the difference Galois group. So you have an assumption of the algebraic collection that satisfy Y, and you find a conclusion on the algebraic and differential relation that satisfy Y. So it's a much more stronger conclusion than expected. What is inside this result is we have a classification of a differentially algebraic group with the IC closures that are SLN. And Cassidy proves that either this group is maximal, so we are in this situation, either this group is constant with respect to the derivation. And Charlotte Ardouin and Michael Singer prove that this last thing is equivalent to the fact that Y is solution of a linear differential equation. And then we use the result before to prove that if Y is solution of a linear functional equation and a linear differential equation, then Y is too simple. But it contradicts the fact that the Galois group contains 7. So when we published this paper, we were extremely happy. And so I've given a lot of talk on the SOM, and people told me that, okay, that's fine, but have you any algorithm to test your assumption on the different Galois group? And the answer is that in general, you have an algorithm by Feng, but it's totally ineffective. So you have algorithm for order 2 and 3. But for general order, you have no reasonable algorithm that you want to apply to test on some functional equation. So we have to work harder. And this was the purpose of this paper with Boris Adamczewski and Charlotte Ardouin. And we are able to delete everything. So without assumption. I mean, either Y belongs to the ground field, either Y is differentially transcendental. So I must insist on the fact that the assumption that Y belongs to a certain field F is extremely important. So, for instance, in the Malarian case, you want to avoid the fact that F could have a logarithm inside. In the shift case, you want to avoid the exponential. The reason why with Charlotte Ardouin and Boris Adamczewski, we consider formal series at infinity. You have no exponential in that. And the goal of this talk is to explicit a new result that I have made last year about the case S. So let me just remind that the case S is Y, a meromorphic function of C, that is solution of a linear functional equation. Okay, so why we did not make the case S with Boris Adamczewski and Charlotte Ardouin? There are two reasons. So the first one is the presence of the exponential. So it's a meromorphic function on C, and it's a differential algebraic. So what a pity! It's that's life. So you can't, if you want to, instead of taking formal series as infinity, if you want to consider meromorphic function on C, you have to deal with the exponential. You have no choice. And the second problem, which may be more serious, is that you have a lot of functions that are meromorphic on C and that are row periodic. And so this field is very huge, and some of them are differentially transcendental and some of them not. So you can't expect results so precise like either Y belongs to a small thing, either Y is differentially transcendental. So let me give the statement of the main result. So consider the field of LH periodic function. So I recall that rho is the map that sends Y of Z to Y of Z plus H. So this is just functions that are LH periodic. And I consider Y a meromorphic function of C that is solution of such equation. And I will consider the following ring. So you consider a polynomial having coefficients that are rational function in Z with coefficients that are LH periodic for some L. And inside the bracket, you have some exponential. And the result is that either R is differential transcendental, either I belongs to the small ring, that is that Y may be written with exponential and LH periodic function. So it's not an if and only if like before, meaning that you have a lot of functions in this ring that are differential transcendental. In fact, they belong to this field here. But that's still an information. Okay, no question so far? So I may continue. So first, I will make some reminder of difference Galois theory. And then I will make the entire proof so I will sketch the proof in the case n equals 2, because it gives you an idea of what is the proof in the general case. And then I will super sketch the proof in the general case, meaning that I will not give the details because I have only 15 minutes, I guess. So I need to hurry. So I expect that some of you are used to difference Galois theory, but maybe some of you are not used to it. So let me give some reminders. And if you are very used to the Galois theory of difference equations, so I will take you back on the next session. So every section has a color, so you can sleep until the end of the blue section. So let Y be a solution of a functional equation. So I will divide by the higher order term, and I want to have a really order n equation. So without loss of generalities, I may assume that A0 is not 0. And let me see the equation as a system, because it's much more friendly to handle with system. So it was the reason why I consider AN equals 1, because the companion matrix is much more simple to write. Okay, and the Picard-Vessier extension, which is the analogous of the splitting field for difference equation, tells you that you have a unique ring extension, or such that you may build a fundamental solution inside R. It means that you have U, a matrix having equation R that is inversible. That is solution of your functional system on R, generated over C of Z by U and the inverse of the determinant. So by U, I mean the entries of U. And the difference ideal, I mean the ideals that are stable under rho. The only such ideals are 0 and R. Okay. And now, so this guy is unique, exists and unique. And now I may define the Galois group. So it's the automorphism of R leaving C of the invariant that commutes with rho. Okay, and we have the image of the difference Galois group into a subgroup of Gn of C. So the fact that you fall into Gn of C, it's a consequence of the assumption of the ideal. So you have sigma to U minus 1 sigma U. And the totally non-trivial fact is that this image is an algebraic subgroup of Gn of C. In fact, this group encodes the algebraic relation among the entries of U. Bigger this group is, and fewer relation you have. Okay? And we have a very useful properties in difference Galois theory that is extremely useful to compute the difference Galois group. I mean, you may perform a change of variable. I mean, I may change y by t times y, and it's a straightforward computation to find that you transform this system into this one. And the very important fact is that you have a Gauss transformation, so variable change, t, such that your system is a CZ point of J. So that means that if your Galois group is diagonal, then you have variable change that transform your system into a diagonal system. If your Galois group is upper triangular, then you have variable change that force your system to be triangular. So we are going to play with that theorem in what follows. So now you can, if you are a specialist of different Galois theory, you can wake up because let me sketch the proof the n equals 2 case. So let y be a meromorphic function of C, that is solution of an affine under one equation. So with A belongs to C of Z and B that belongs to the ring that I given a few slides before. So R is a ring made with exponential and H periodic function. So either Y is differential transcendental, so either Y belongs to a small ring. So if we take B a rational function, you may iterate the whole equation, and then you will find an homogeneous equation of order 2. So 1b is a rational function. We are in the setting of the framework in the case order 2. So this result stay true if you consider B in that ring, for reasons that will appear in few slides if I'm able to do it. But not sure because time is going away. So now consider really the order 2 case. So let J be the Galois group. So it's an algebraic group of GL2. And we have a lot of theorem of classification of such a group. So J may be finite, but when J is finite, the functions are algebraic, and in fact we have chosen quite carefully the different ring in order to avoid that case. So J is automatically infinite, and J may be conjugated to a subgroup of upper triangular matrices. J may be conjugated to a subgroup of J dual group, or J must contain SL2. So in the two first cases, I say conjugated because the definition of J as a subgroup of GL2 of C depends on the choice of the fundamental solution, U. If you take another fundamental solution, you will find a group that is conjugated to the first one. So it means that if you take the good fundamental solution, then you will be on that form. Okay, so let me consider the case 1. So assume that y is differential algebraic, and then I need to prove that y is very simple. So if y is 0, the result is obvious. So let me assume that y is not 0. Variable change that transform your system into a triangular system, because we are in the case where the system is upper triangular. And I consider v1, v2, the new variables. So if y is differential algebraic, then v1 and v2 have to be differential algebraic. And if y is morphic over C, it's the same for v1 and v2. So in some sense, I'm just saying that instead of considering an arbitrary equation, in that case, I may considering triangular situation. So let me make the equation of v2. So if you look carefully, so rho of v2 equals c times v2. So, and since V2 is differential algebraic, because Y is, we use the order 1 case to prove that V2 belongs to the small ring. And then you consider V1, that is solution of an affine order 1 equation, and the second member have coefficient, the inhomogeneous order have coefficient R, because V2 belongs to R. And then you may prove similarly that with the affine case that V1 belongs to R. And if V1 and V2 both belong to R, you may multiply by T minus 1 to the left, and you arrive at the conclusion that Y belongs to R. Okay, so now the case 2. So assume that it's differential algebraic and we are not in case 1. So this time I have transformations that transform the system into an anti-diagonal system. And this time V1 will be solution of a row 2 equation of order 1. But everything that I say for row is still correct for row square. It's just you replace h by 2h. So this time I apply the order 1 case to deduce that V1 V1 belongs to R. And if you look at this equation, so Y is solution of an affine order 1 equation with an inhomogeneous member belongs to R. So Y belongs to R. So it was one of the reasons why we need an homogeneous member that belongs to R to handle this va-et-vient between Y and V1, V2. So you first prove that V1 belongs to the good ring, and then you come back to Y. So if V1 and then V2 belongs to R, then again you multiply to the left by T minus 1. And you arrive at the conclusion that you want. In the last situation, so J contains SL2, so it's the big difference Galois group case. And in that case, either Y is holonomic or differential transcendental. It's the use of the classification by Cassidy of a differentially algebraic group. And if Y is holonomic, by Schaeffer-Singer, Y belongs to the very small field because they also deal with the case S. So they prove that in that situation you are exponential. And then you are done. And when J contains SLN, it's a little more tricky. You have to make something to go back to the case SL2, but that's not so complicated, and I want to advance, so consider that it's okay. And so with the last minutes that I have, so if I'm aware I have 5 minutes, so it should be okay. Let me give the proof, some sketch of the proof in the general case. So in the general case, it's a very similar path to the paper we made with Boris Sadowski and Charles Tardouin, but each step you have to be much more cautious. So there is this first result that says that so I say J is irreducible. It's irreducible as an algebraic group, meaning that you have no finite vector subspace of Cn that are stable under J. So if J is irreducible, then you obtain automatically that Y is differential transcendental. So it's so here the proof is very similar to Dreyfus and Tardouin, and it's in the reducible case that the proof is quite different. So assume that Y is differential algebraic, and again, the goal is to prove that Y has to be too simple. So again, is Y is 0, then the root is obvious, so let's assume that Y is not 0. If the system is irreducible, it's okay. So now let me assume that the system is reducible. And a consequence of this theorem is that when the Galois group is reducible, then it's conjugated. You may find a Gauss transformation that puts your system into a block triangular system. So I may transform my system into a system of this form. So A1 and A2 are square matrices. So the size of A1 corresponds to the size of block of the reducible block. And we have to take separately two situations. So when A1 has size bigger than 1, so in fact, taking a smaller reduction of this kind, we can assume that A1 has minimal dimension, and then we find that A1 has to be irreducible. And so if A1 has size bigger than 1 is a irreducible case that I've given just before. So I told you that that the entries have to be in the small ring. And in fact, if you look carefully on the entries of Y, the last entries are just solution of the smaller equation. So in fact, in this situation where the system is reducible, it just means that it's equivalent to a smaller one. And it gives you the will to make an induction on the order of the equation. And very surprisingly, that works. And in fact, so there is this dichotomy, either A1 has dimensions strictly smaller than 1, and then it's the induction step, and you arrive at the conclusion. Either A1 has dimension 1, and then you are in the situation of the affine case, order 1 affine case, and then you arrive at the conclusion. So So the general idea is that the path of the proof is similar, but each time you have there is a difficulty. So, and before finishing this talk, let me make a comment. So here we have treated the case S. So the idea was to add some function that are counterexample in general. So here we have added the exponential. It could be interesting to see the case Q prime and N prime, where we add functions that are differential algebraic and see what we can do. So for instance, here we like towards the logarithm, here the theta function. In fact, the fact that every function that I have given, every counterexample function that I have given, a solution of order 1 equation, it's not a random fact because we make an induction proof. So if the theorem fails, it fails at the order 1 case. So a further work should be to consider a general setting of F, very huge, that contains all solutions of order 1 equations that are differential algebraic, so all the possible counterexample, and see if it's possible to give a statement. So in the full generality, it seems to be quite complicated, but maybe something more general than this could be done. So I have finished 40 minutes, and thank you for your attention. If you have questions, I'm here.
Thank you very much for your interesting talk. Are there questions? Please just unmute yourself or write in the chat.
I have a question if I may.
Please.
Okay.
You had listed the list of all the cases besides the S prime case that you consider, I think in your slide 6. And you just made some comments about it. I want to make sure that I understand. Somehow in the in the so this case S is the only one out of the four that is somehow global, right? The last three cases are looking at a field of local series at some fixed point of your operator, and
Yeah.
I don't know if it's the same or a different generalization of what you have in case S to consider in cases S prime and Q and M somehow a field of meromorphic functions, maybe meromorphic functions away from some bad points or something, and see which meromorphic functions could possibly be both row finite and differentially algebraic. Do you have any ideas about what that would look like, or is it maybe related to what you were discussing? It wasn't very clear to me.
So in the shift case, so the fixed point is infinity. So meromorphic function of C is just meromorphic function outside the fixed point. In the Marian case, the Puiseux series are in fact convergent in the unit disk. Let's say that. So you mean what happens if I replace f by a field of meromorphic function somewhere?
Yeah. So for a concrete example, in case Q, one could hope that something like this, right, where you replace f with meromorphic functions on C without zero.
Yeah, C star.
And then you have to throw in all the elliptic functions and then maybe a little bit more, right?
Yeah. So this could be the case Q prime. And so there is this theta function. It's so this Q theta function is meromorphic on C star and this differential algebraic. So we will have this same kind of problems than in the case S. It might be not too trivial because at some point I need this theorem. So the dichotomy between being holonomic, non-holonomic, and being trivial for the case Q prime. So, for instance, in the case S, Schafke and Singer prove that if meromorphic function of C is holonomic, then it's polynomial in exponential. So we should be able to prove something like if you are holonomic, then you are, I don't know, polynomial in Q theta function or something like that. But they are not holonomic. So I have no idea of what will be the statement in the case Q prime.
Great. Thank you.
But it's an interesting question that we will have to do that someday.
There's a question in the chat which you may either read or I will read it
Yeah.
out now. So a question posed by Bertrand Teguia. Thank you for your nice talk. Perhaps a general question. Do you think you can derive a kind of measure for the transcendentality of a function solution to a shift equation, like the irrationality measure in the case of irrational numbers?
To be honest, I have no idea. Yeah, that's a tough question. Perhaps, but I have no idea of how to do that.
Okay, are there other questions? So Bertrand writes, thank you.
You're welcome.
Just unmute yourself or write in the chat. If this is not the case, then I stop the recording. And we thank Thomas again for the very interesting talk. And
thank you.
And I guess we resume next week, next Friday. Thank you.
And so now I have a new term